What if the three-dimensional world you inhabit, with all its depth and volume and substance, is actually a projection from a two-dimensional surface you cannot see? This isn't a metaphor. This isn't poetry. This is a serious proposal emerging from the mathematics of black holes and quantum gravity, and it suggests something so strange about the nature of reality that even physicists who work with it daily find it difficult to fully internalize. The universe, at its most fundamental level, may be holographic. All the information that describes everything happening in a volume of space might be completely encoded on the boundary of that volume, on a surface with one less dimension. Your body, your thoughts, the stars, the vast cosmic web stretching billions of light years, all of it might be a kind of three-dimensional projection of information living on a distant two-dimensional screen. Before you dismiss this as science fiction, let me be clear about what we're discussing. The holographic principle is not fringe physics. It's a well-studied theoretical framework that has emerged from rigorous mathematical investigations into black holes, quantum mechanics, and the structure of spacetime itself. While we don't have direct experimental confirmation, we have strong theoretical reasons to take it seriously. The evidence is mathematical, deep, and accumulating from multiple independent directions. Let's start with something concrete that will help you understand why physicists even entertained this idea in the first place. Think about a hologram on a credit card or a museum display. It's a flat two-dimensional surface, but when light hits it the right way, you see a three-dimensional image floating in space. The entire three-dimensional picture is encoded in the interference patterns on that flat surface. Every point on the hologram contains information about the entire three-dimensional scene, just scrambled up in a particular way. If you cut a hologram in half, you don't get half the image. You get the whole image from a slightly different perspective with lower resolution. Now, the holographic principle suggests that something analogous happens with physical reality itself. But we're not talking about light and interference patterns. We're talking about quantum information, entropy, and the fundamental degrees of freedom that describe physical systems. The claim is that all the information needed to describe what happens inside any region of space can be encoded on the boundary of that region, and that the three-dimensional physics we observe emerges from this two-dimensional encoding. This idea didn't come from nowhere. It emerged from a deep puzzle about black holes that forced physicists to rethink the relationship between information, space, and gravity. In the early 1970s, researchers discovered something remarkable about black holes. They have entropy. Now, entropy is a measure of the number of microscopic states a system can be in while still looking the same from the outside. A hot gas has high entropy because its molecules can be arranged in countless different ways while maintaining the same temperature and pressure. Entropy is fundamentally about information, about hidden microscopic complexity. The strange thing about black holes is that their entropy is proportional to the area of their event horizon, not to their volume. The event horizon is the boundary beyond which nothing can escape, and it's a two-dimensional surface surrounding the black hole. If you imagine a black hole as a sphere, its volume goes like the radius cubed, but its surface area goes like the radius squared. For any ordinary three-dimensional object filled with matter and energy, we expect the entropy to scale with volume, because entropy should count the number of ways you can arrange stuff inside the object. But black holes don't work that way. Double the radius and you increase the volume by a factor of 8, but the entropy only goes up by a factor of 4, tracking the surface area. This is profoundly strange. It suggests that the maximum amount of information that can be contained in any region of space is determined not by the volume of that region, but by the area of its boundary. It's as if the three-dimensional interior is somehow redundant, and all the real information lives on the two-dimensional surface. This observation led to the holographic principle, first articulated as a general proposal in the mid-1990s. The principle states that the description of a volume of space can be thought of as encoded on a boundary to that region, preferably a light-like boundary such as a gravitational horizon. But this raises immediate questions. How can three-dimensional physics be encoded on a two-dimensional surface? What does it mean for something to be encoded this way? And if we live in three dimensions, why don't we notice that we're actually holograms? To understand this, we need to look at a concrete example where the holographic principle has been realized mathematically with complete precision. This is the AdS-CFT correspondence discovered in the late 1990s. AdS stands for anti-de Sitter space, which is a particular kind of spacetime with negative curvature, a bit like a saddle shape extended into higher dimensions. CFT stands for conformal field theory, which is a type of quantum field theory with special symmetries that doesn't include gravity. The correspondence is an exact mathematical equivalence between a theory of gravity in a higher dimensional AdS spacetime and a quantum field theory without gravity living on the boundary of that spacetime. Let me be precise about what this means. Imagine a five-dimensional universe shaped like anti-de Sitter space. It has a four-dimensional boundary at infinity. The AdS-CFT correspondence tells us that everything that happens in the five-dimensional bulk, including gravitational phenomena like black holes and gravitational waves, is exactly equivalent to processes in a four-dimensional quantum field theory on the boundary. Every particle in the bulk corresponds to a field in the boundary theory. Every black hole in the bulk corresponds to a hot, thermalized state in the boundary theory. The correspondence is so precise that you can calculate quantities in one theory and translate them exactly into the other theory, and you get the same answers. This is not a metaphor or an approximation, it's an exact duality. The five-dimensional gravitational theory and the four-dimensional non-gravitational theory are two different descriptions of the same physics. They're like two languages describing the same reality. An observer living in the bulk would experience gravity, curvature of space-time, and could fall into a black hole. An observer in the boundary theory would experience no gravity at all, just quantum fields interacting according to quantum mechanics. Yet these are the same physical system described from different perspectives. Now, AdS-CFT is formulated in anti-de Sitter space, which is not the universe we actually live in. Our universe appears to have positive cosmological constant and is expanding, more like de Sitter space than anti-de Sitter space. So we cannot directly apply AdS-CFT to describe our reality, but the existence of even one precise example where holography works perfectly tells us something profound. It shows that holography is not just a vague idea, but a concrete, mathematically consistent feature of quantum gravity. It demonstrates that space-time can emerge from quantum field theory, that an extra dimension of space can appear as a kind of encoded structure in the correlations and dynamics of a lower dimensional theory. This connects to something deeper about information and entropy in quantum systems. In quantum mechanics, the state of a system is described by a wave function, or more generally by a density matrix. The amount of information in a quantum state is measured by entropy. For a pure quantum state, the entropy is zero. There's no uncertainty, you have complete information. But if you only have access to part of a quantum system, you describe that part with a reduced density matrix, and it will generally have non-zero entropy called entanglement entropy. This entropy measures how much the part you can see is entangled with the part you can't see. Here's where it gets interesting. In quantum field theory, even in empty space, the vacuum state is full of quantum fluctuations and correlations. If you imagine dividing space into two regions separated by a boundary, the quantum fields on one side are entangled with fields on the other side. You can calculate the entanglement entropy of one region by tracing over the degrees of freedom in the other region. And when you do this calculation in quantum field theory, you find that the entanglement entropy is proportional to the area of the boundary between the regions, not the volume of the region. This is remarkably similar to black hole entropy. In both cases, entropy scales with area rather than volume. This suggests a deep connection. Perhaps black hole entropy is really entanglement entropy. Perhaps the information content of a region of space-time is fundamentally captured by the entanglement between quantum degrees of freedom inside and outside that region. And perhaps this is why holography works, because the information content of a volume is actually encoded in the entanglement structure at its boundary. In the AdS-CFT correspondence, this connection can be made precise. The entanglement entropy of a region in the boundary theory can be calculated using a beautiful geometric formula in the bulk theory. You find a minimal surface in the bulk that corresponds to the boundary of the region, and the area of that minimal surface, measured in appropriate units, gives you the entanglement entropy. This is called the Ryu-Takayanagi formula, and it provides a concrete link between geometry in the bulk and quantum information in the boundary theory. Space-time geometry emerges from the pattern of entanglement in the quantum state. Think about what this means. In the boundary theory, there is no geometry, no space in the usual sense. There are just quantum fields at points on the boundary interacting and becoming entangled with each other. But when you look at the large-scale structure of these entanglements, when you coarse grain over the microscopic details, a geometric description becomes useful. The pattern of which regions are highly entangled and which are weakly entangled can be represented as a curved spacetime in one higher dimension. Regions that are nearby in the emergent geometry correspond to boundary degrees of freedom that are strongly entangled. Regions that are far apart correspond to weakly entangled degrees of freedom. Distance in space emerges from entanglement in the quantum state. If you could somehow cut all the entanglement between two regions of the boundary theory, the corresponding regions in the bulk would become infinitely separated. The spacetime would tear apart. Conversely, if you increase the entanglement between two regions, you bring the corresponding bulk regions closer together. There's a slogan that captures this: spacetime is entanglement. Now let me be clear about what is established and what remains speculative. The AdS-CFT correspondence is extremely well established within string theory. Thousands of calculations have been done, and the duality holds up with extraordinary precision in the contexts where we can check it. The Ryu-Takayanagi formula relating entanglement and geometry has been extensively verified. These are not wild guesses, they're robust mathematical results. What remains speculative is whether holography applies to our actual universe. AdS-CFT works in anti-de Sitter space, not in the expanding universe we inhabit. Researchers are working on extending holographic ideas to cosmological settings, but we don't yet have a complete holographic description of our universe. We don't know exactly what the boundary theory would be, or where the holographic screen is located. Some proposals place it at the cosmological horizon, the boundary of the observable universe. Others explore different possibilities. This is active research, not settled science. But the black hole results are more firmly established. The Bekenstein-Hawking entropy formula, which relates black hole entropy to horizon area, follows from combining general relativity with thermodynamics and has been confirmed through multiple independent approaches, including string theory calculations that reproduce the formula from microscopic counting of states. We have strong theoretical reasons to believe that black holes really do have entropy proportional to their horizon area, and that this entropy represents genuine information about the quantum state. This brings us to the black hole information paradox, which provides another compelling argument for holography. When a black hole evaporates through Hawking radiation, what happens to the information about what fell in? In quantum mechanics, information is never destroyed. The evolution is unitary, meaning that the quantum state at any later time uniquely determines the state at any earlier time. But Hawking's original calculation suggested that black holes radiate purely thermal radiation, which carries no information about what fell in. The black hole would evaporate completely, and the information would be lost, violating unitarity. This paradox has driven enormous amounts of theoretical work over the past 50 years. The resolution appears to involve subtle quantum correlations in the Hawking radiation that encode the information about what fell in, correlations that emerge when you properly account for the quantum nature of space-time itself. The holographic principle plays a crucial role in this resolution. If all the information about the black hole interior is encoded on the horizon, then as the black hole evaporates and the horizon shrinks, that information can be gradually transferred to the outgoing Hawking radiation. The information never needs to travel from the interior to the exterior through the event horizon. It's already on the horizon in encoded form. Recent work has sharpened this picture considerably. Calculations using AdS-CFT have shown explicitly how information escapes from evaporating black holes in the holographic dual theory. The quantum state of the radiation becomes increasingly entangled with what remains of the black hole, and eventually the entropy of the radiation begins to decrease as the black hole approaches complete evaporation, following what's called the Page curve. This is exactly what unitarity requires, and it can be calculated using the tools of holographic duality. But let's return to the original question. If the universe is holographic, what does this mean for us? Are we, right now, holograms? In what sense could this possibly be true? The answer depends on what you mean by hologram. You are not an optical hologram made of laser light. You are made of atoms and molecules, and those atoms are made of quarks and electrons, and all of this is extremely real in the operational sense. The holographic principle doesn't claim that your body is somehow fake or insubstantial. What it claims is that the information describing your body and everything else in a region of space can be encoded on the boundary of that region. Think of it this way. You can describe the world either in terms of what's happening in the bulk, with particles and fields and space-time curvature, or in terms of what's happening on the boundary, with a different set of degrees of freedom and dynamics. These are two different but equivalent descriptions. An observer like you, embedded in the bulk description, naturally uses the bulk language. You perceive 3 dimensions of space, you experience gravity, you move through space-time. But in principle, everything about your experience could be captured in the boundary description. Your thoughts, your memories, the patterns of neural firing in your brain, all the information is there in both descriptions. This is conceptually similar to how you might describe a fluid either in terms of molecules or in terms of temperature, pressure, and flow velocity. The molecular description and the hydrodynamic description are both valid. Neither is more real than the other. They're just different levels of description suited to different purposes. The holographic principle suggests that bulk and boundary descriptions are related in a somewhat analogous way, though the relationship is more profound because the bulk description has an extra dimension that doesn't exist in the boundary description. One way to think about this is through the lens of emergence. Just as temperature emerges from molecular motion, space-time might emerge from quantum entanglement. Just as fluid dynamics emerges from particle physics, general relativity might emerge from quantum field theory. The 3-dimensional universe with gravity would be an emergent, effective description that arises when you coarse-grain over the microscopic degrees of freedom of the holographic theory. This has strange implications. For one thing, it suggests that the number of fundamental degrees of freedom in the universe is finite. The entropy of the observable universe, if it's dominated by the cosmological horizon, would be proportional to the area of that horizon. This is an enormous number, something like 10 to the 120 bits of information, but it's finite. In a truly 3-dimensional universe, with infinitely many points in space, you might expect infinitely many degrees of freedom. Holography says no. The real count is limited by the boundary area. It also suggests that spacetime is not fundamental in the way we usually think. We imagine that space and time form an independent arena in which matter and energy move around and interact. But if spacetime emerges from the holographic encoding, then spacetime is more like a useful computational tool, a way of organizing information about correlations in the fundamental theory, rather than the bedrock of reality. The real bedrock would be the quantum state and its entanglement structure. This connects to broader efforts in theoretical physics to understand quantum gravity. Both string theory and loop quantum gravity, the two main approaches to quantizing gravity, suggest in different ways that spacetime is not fundamental. In string theory, spacetime geometry emerges from the collective behavior of strings and branes. In loop quantum gravity, spacetime has a discrete structure at the Planck scale, a kind of quantum foam from which classical geometry emerges at larger scales. The holographic principle fits naturally into this picture. It's one piece of the larger puzzle of how space-time arises from quantum mechanics. There's also a philosophical dimension to this that's worth considering carefully. If the holographic principle is correct, then the ontology of the universe, the question of what really exists, becomes subtle. Do the bulk and boundary both exist, or is only one of them real? Are we discovering that the universe has fewer dimensions than we thought? Or are we discovering that dimension itself is a malleable concept that depends on your descriptive framework? Physics doesn't necessarily answer these ontological questions. It tells you what mathematical structures successfully describe reality, but it doesn't always tell you which description is the true one in some metaphysical sense. The holographic duality might be epistemological rather than ontological. It might be about two equally valid ways of knowing the same reality, rather than about reality secretly being one way rather than another. Or it might be telling us that reality doesn't have a unique intrinsic dimensionality, that asking whether the universe is really 2-dimensional or 3-dimensional is asking the wrong kind of question. These are deep waters. But they're worth exploring because they reveal something important about how physics works. We build mathematical models that successfully predict observations, and sometimes we find that wildly different models predict exactly the same observations. At that point, the question of which model is true becomes ambiguous. Maybe both are true. Maybe truth is not unique. Maybe reality is the invariant structure that persists across all empirically equivalent descriptions. The holographic principle also raises questions about consciousness and observation. If you are a hologram, if your entire neural structure and mental state can be encoded on a two-dimensional surface, does that change anything about your subjective experience? Almost certainly not. The encoding doesn't affect the functional relationships between parts of your brain, the causal structure of your thoughts, the flow of information through your nervous system. Whether that information is fundamentally stored in 3 dimensions or encoded on a two-dimensional boundary doesn't change the subjective character of experience. But it does raise interesting questions about the relationship between information and consciousness. Some theories of consciousness focus on integrated information, on how much a system processes and integrates data about its environment and itself. If consciousness arises from information processing, and if the information content of your brain is fundamentally holographic, then perhaps consciousness has a holographic character as well. This is speculative, and I want to be clear that we have no established theory connecting consciousness to the holographic principle, but it's an intriguing direction for future thought. Let me also address a common misconception. The holographic principle does not mean that we live in a simulation. A simulation is a computational model running on some external hardware, like a video game running on a computer. The holographic principle is a statement about the mathematical structure of physical law itself, not about the universe being computed by something outside it. There's no programmer, no external machine. The universe, whether described holographically or not, is the fundamental reality. It's not a copy or a simulation of something else. That said, holography does suggest that physical law has a computational character. The evolution of the boundary theory can be thought of as a kind of computation, processing quantum information according to specific rules, and the emergence of bulk spacetime from this computation has a somewhat computational flavor. The geometry is encoded in correlations, and observables in the bulk can be calculated by processing boundary data. So while the universe is not a simulation in the literal sense, it may have deep structural similarities to computational processes. This is an area where physics touches computer science and information theory in fascinating ways. We're still in the early stages of understanding what holography really means. Most of our concrete results come from AdS-CFT, which applies to a universe that's not quite like ours. Extending holography to cosmology, to our actual expanding universe, remains a major challenge. There are proposals, like the AdS-CFT correspondence, attempting to describe de Sitter space holographically, but these are far less developed than AdS-CFT. We don't yet know if there's a holographic dual to our universe, and if there is, what its boundary theory looks like. But the direction is clear. Multiple lines of evidence, black hole entropy, AdS-CFT, entanglement entropy, the information paradox, all point toward the same conclusion. The information content of space is finite and bounded by area. 3-dimensional physics can be encoded in 2-dimensional quantum information. Space-time and gravity emerge from entanglement structure. The universe, in some precise mathematical sense, is holographic. This is not established fact in the way that electromagnetism or quantum mechanics are established. We don't have direct experimental evidence for holography in our universe. What we have is a compelling theoretical framework that solves deep conceptual problems, that has been verified in specific contexts, and that points to a profound restructuring of how we think about space, time, information, and reality. And perhaps that's the deepest lesson here. Reality may not be what it seems. The 3-dimensional world of our experience might be an emergent holographic projection. The information that defines us might live on a distant boundary we cannot perceive. The very fabric of space-time might arise from quantum correlations that have nothing to do with geometry at the most fundamental level. We are still learning what the universe is made of, what it means for something to exist, what the relationship is between mathematics and physics and consciousness. The holographic principle is one piece of this larger puzzle. It tells us that the universe is stranger and more subtle than classical physics ever imagined. It suggests that the ultimate nature of reality lies not in things located in space, but in information, in pattern, in the abstract structure of quantum correlations that manifest as the concrete physical world. We stand at the boundary between knowing and not knowing, between the universe as we perceive it and the universe as it fundamentally is. That boundary is where physics lives. And if the holographic principle is correct, then reality itself is a kind of boundary phenomenon, a surface expressing depths we're only beginning to fathom. Think about that deeply. And if these questions call to you, if you want to continue exploring the mathematical structures underlying existence, join us here at Susskind Point as we trace the boundaries of what can be known.